All right, so now we're slowly getting into derivatives, okay? We're talking about average rates of change, and we're going to compare this with instantaneous rates of change. So in calculus, a lot of the time, we're interested in seeing how one variable changes in relationship with another. So, think about some of the examples that you did in your tutorials. You have the rate of an illness being modeled by an exponential function. Okay, so that's a function where it talks about, the population getting sick with respect to time. So sometimes we want to see how that changes depending on what time interval or what position in time you're in. So here we're going to discuss the average change. And when we learn about derivatives, or it'll kind of lead into derivatives, we'll discuss the instantaneous rate of change. So in terms of definition, again, this just means that we have some function, real valued function. That's what it means in English. And we have these values a and b. So our average rate of change, in terms of notation, there isn't really like a symbol for it. Average rate of change, so that's just typically what I write, of this function f of x with respect to, so what this means is I'm interested in values of x that are in between a and b, including a and b. The average rate of change is we plug in b into our function, we subtract off what a is, and then we divide that by a over b. Notice that this formula is equivalent to looking at the change in y over the change in x, which is equivalent in notation. If you don't want to write this in English, you can write it like this. But this is equivalent to having 1 point y2 minus y1. So this would be y2, or f of b, or f of a would be y1. And then I have x2 minus x1. And this is just the definition of a slope. So let's say that we have this function f of x here. Okay, now let's say that we pick 2 points. Okay, let's say that we pick an a and a b, and we're going to just assume that our a is going to be less than b. So say I pick these 2 points, a and b. Now these correspond to different y values. Okay, so the name of the first y value would be f of a. The name of the second y value would be f of b. And if I wanted to look at my slope, or the average rate of change of this function between these 2 points, I'm just going to take a line to connect them. So I need to go through this point, and that's not too bad. Okay, so this line right here, this represents the average rate of change between this point and this point. And if we wanted to calculate what this pink slope was in between a and b, we also know how to do that. That's just rise over run. Okay, so we make this little triangle here. This is just run, this is just rise, which is just the equation to find the slope of a line in general. This is also an example of a secant line. Now, how does this compare to an instantaneous rate of change? So this is looking at how a function is changing within a certain interval. But now, what happens if I want to, say, consider the rate of change at this point right here? What would I have to do? Well, what I could do is I could move this secant line up a little bit more. And now, the points I'm looking at are here and here. So that interval a and b and the corresponding y values of it have just gotten smaller. Okay, so now we're looking at this strip here. So that will give me an answer that's closer to the value here, but that's still not good enough for me. So I want to see the rate of change at that red point. So if I take an even smaller interval, I'm getting closer. But as my interval here, my a and b gets closer and closer to each other. Okay, these green lines will get closer and closer to each other. And then we'll eventually be able to look at now what's called the tangent line. Okay, so we can look at the point right here, and we basically find it by having A and B get closer and closer together. So this itself is like a limit. What happens in the limit as B approaches A? So if we do this, this is looking at the instantaneous rate of change at this point here, which I'll just call it C. Okay, so now this is looking at the tangent line, and this is an instantaneous rate of change. This is the same as looking at the slope of a tangent line. And there's actually two definitions. So we're going to do one that corresponds first with our picture, and then we'll write down the one that looks more like a derivative. So we're going to have f be a real valued function, okay, which means that we take things to r and map them to r. And we're going to have our real values a and b. So the instantaneous rate of change, instantaneous rate of change for f when x is equal to a is, so if we look at the average rate of change, we have our f of b minus our f of a divided by, divided by b minus a. And if we were interested in the instantaneous rate of change at a, I would want to take my b and move it closer and closer and closer and closer until I eventually reach the same position. Okay, so what is that? That can be described in calculus using a limit. So if we take the limit as b approaches a of this whole thing, this is our instantaneous rate of change. Okay, and we'll write this as instant rate of change. Okay, and we're going to put a big green box around this. Whoops, because you will need to know it. Good enough. I'll fix it afterwards. So this is one way we can define it. The way that you've probably seen it is using the h. So another way we can phrase this is we're looking at the limit as h goes to 0 of f at the point of interest a, and then we say plus a little bit, minus f at a, all divided by h. Okay. These mean the same thing, but the one that you're probably going to want to get used to is the one with the h, because we're going to be defining derivatives with this. All right, so let's say that we have a distance function. So the distance, we're going to call it s of t. Okay, for distance, for whatever reason, they usually use s's. S of t is equal to 2t squared minus 5t plus 40. So for the first part, what we're going to do is we want to find the average velocity or average speed to 4 seconds. All we're going to do is we're just going to use our equation. So s of 4 minus s of 2, and then our b and a is just going to be 4 minus 2. So thus our average velocity is what? Is 7. Okay, so this upper part here, these s's, you can think about these as having dimensions that correspond with kilometers, and the 4 and 2, this corresponds with dimensions in time or seconds. Now we're going to find the instantaneous velocity at 4 seconds. Let's first write our expression, our equation. So our instantaneous velocity, this is going to be equal to, so this is when we consider a limit. So we're going to go the limit as h goes to 0, The function that we're talking about here is s, and I'm interested at the point 4. Okay, so 4 plus h minus s of 4, all divided by h. Now let's plug this in. Now remember, when you're doing these problems, you have to keep writing the limit. Okay, so I am left with, do I have room? I have enough room here. The limit as h goes to 0 of 2h plus 11. And then as my limit goes to 0, this is just going to give me 11. T is equal to 4 is 11 kilometers per second.